We're talking about, we just finished up talking about Le Chatelier's principle. And again, as we talked about, the idea here is really you're going to do something to the equilibrium that will mess up the equilibrium. It will cause really the reaction to shift one way or the other. And really the ultimate goal there is for it to try to get back to that equilibrium state. So remember that ultimately what's causing the shift to occur in most cases is either you made more reactants, which would cause the forward reaction to occur. You maybe made more products, which would cause the reverse reaction to occur. Or you removed reactants, which means you had more products that caused the reverse reaction to remove. Or you removed some products, which causes the forward direction to occur. We talked about the meaning of K, and again, a reminder that anything above 1 is considered a large value of K. And again, you would essentially have a lot more products at equilibrium, especially if you have a really large value. And obviously, the small value of K means the opposite. You should be hanging out on the reactant side, probably have mainly reactants there at equilibrium. And the reaction, for the most part, is probably not actually occurring. It's not really going to the product side. It's just hanging out there on the reactant side. Um, if you do want to calculate the actual value of K, it does need to be equilibrium concentrations that go into the expression to calculate it. And again, as we talked about, if it goes to the right, we should have a large value of K and a small value there as well. Now, in this case, at a given temperature, calculate the equilibrium if our equilibrium concentration of H2 if we have 1.5 times 10 to the minus 2 and 5 times 10 to the minus 1. This is just using our expression here. Our K is equal to our HI squared divided by our H2 and our I2, and that equals 50. And if these are equilibrium concentrations, we basically would put them in as we did down here. So our HI is 5 times 10 to the minus 1, and we would square it, divided by our H2 that we're looking for, and our concentration there of I2, which is 1.5 times 10 to the minus 2. So these would be, again, equilibrium concentrations because we're able to go in there, basically doing the math there and solving for H2. It looks like we get a value of 0.33. Again, to solve for H2, these two guys are going to switch places. So H2 should equal our 5.0 times 10 to the minus 1 squared divided by 50, and our 1.5 times 10 to the minus 2. So if we put those values in and grab a calculator, I feel like one of these answers are wrong. So let me just double check here. Let's see here. We got 5 to the minus 1 squared divided by 50 divided by 1.5 to the minus 2. Going to give us 0.33. So that does look right, actually. So that's good. So again, if you do have the actual equilibrium concentrations, you could go in there and you could also solve for somebody else's equilibrium concentration, or again, you could solve for the equilibrium constant value in this case. All right, so let's talk about, though, what happens when you actually do not have equilibrium concentrations given to you and you're asked to actually solve for it. So let's talk about a calculation that you will not see until you go to 1B again, but for some reason they like you to learn it here. All right, so if we have initial concentrations and we want to find equilibrium concentrations, we do have to do a calculation. And the calculation that we use here actually is what is referred to as ice tables. I know, it is that same ice tables that we talked about. So ice tables are what are used basically to solve for equilibrium concentrations. The I there is initial concentration. C is the change. And E is equilibrium in this case. And we use these tables here to basically figure out what everybody's equilibrium concentration is going to be once we reach it based on our initial concentrations. So the one thing that we use for the change is we use the letter X typically is used for the change part of it. And ultimately what we're trying to do is find what X is, and then that will allow us to get to the equilibrium concentrations. So let's say, for example, here we had A plus B goes to 2AB. And let's say that initially for A, we had a concentration of, let's pick a big number there, 2 molar, right? And we'll say initially for B, we will have a concentration of 2 molar as well. So we have these initial concentrations, and we're looking to solve for what is the equilibrium concentration. So to do this, we do an ice table here. And we will start with our initials, which would be 2 molar there, 2 molar there. And now in this particular case, nothing is mentioned to us about the products. So it is safe in that case to assume that you're starting with nothing on the product side. So if they wanted you to start with something on the product side, they would give you a concentration. But in this case, you're going to start with nothing here. We can also write our equilibrium expression for this, and it is our products over our reactants. So this would be AB squared divided by A and B. And I guess I should have gave a value there. Let's just say the value is 10. How's that? We'll go with that. We'll just say we know the K here is 10. My made up question. All right. So the change part's actually the really important part of whenever you do an ice table. The change part tells you how things are changing. And as I mentioned, we typically will use X for this. Now, because we have no products to begin with, the only option for this reaction is it needs to head towards the product side. And again, because we have no products to begin with, so it can't go the other way. So its only option at this point is it has to actually head towards the product side. And what that means is as this reaction progresses, the amount of our reactants, our A and B, should actually start decreasing with time. And the amount of our products, the AB here, should actually be increasing with time. And how we represent that in an ice table is if something is decreasing, which is typically our reactants, we use minuses. And if something is increasing, which is typically our products, we use plus signs. So the change part here, this would be minus X. And we also have to, in the change part, take into account the coefficients, because the coefficients in this case is going to take care of the stoichiometry, the mole-to-mole relationship everybody loves. In this case, though, the coefficient here is a 1, so we just do basically minus 1x. Coefficient here is also a 1, so this is going to be minus x. But the coefficient over here is actually a 2, which means this would be plus 2x in this case. So again, the coefficient goes with our change part. If you do not use the coefficients in the change part, you pretty much did the problem wrong right there. And that's because it will give you the wrong mole-to-mole relationship. You'll have the wrong stoichiometry, and your calculation will definitely be wrong. So it's really important to use the stoichiometry or the coefficients there. What we do at the end here is simply just bring everybody down at equilibrium. This will be 2 minus x, 2 minus x, and 2x. Any questions on the table here? Yeah. Find the coefficient by the negative x? Yeah, so whatever the coefficient is how many x's you have, but essentially mathematically, for example, if you want to figure out what this guy is, you would have to take 2 times the value of x at some point. So you are multiplying. Yeah. but the 2 does come from the coefficient. And again, that basically does kind of the stoichiometry part for you all in one step. Yeah. So the goal here really is to solve for x. So to solve for x, what I'm going to do actually is rewrite up higher there since we're kind of a bad room here. Take this. So initially we had 2, 2, and 0, minus x plus 2x, equilibrium 2 minus x, 2 minus x, and 2x. Our k value here was our ab squared divided by our a and our b, which equals 10. So as I mentioned, the goal here is to really solve for x, and the way we're going to do that is we're going to take everything in the equilibrium line. We're going to actually put it into our equilibrium expression. So everything there goes into our expression. And when we do that, that's going to give us 2x squared divided by 2 minus x times 2 minus x equals 10. Now, in this case, we want to solve for x, and there's a variety of ways at this point that you can solve for x. One way is to use the quadratic formula, which clearly we're not going to do in here because this is not Chem 1b. So when you get to Chem 1b, you can use the quadratic formula. You can also do what is known as successive approximation, which you should just use the quadratic probably at that point if you're going to try that. But really in this case, which is probably the case for our purposes here, you could also do an assumption in some situations. We're going to look at it, and hopefully you will see it's actually a perfect square on both sides. So you can take a big giant square root on both sides, and that's going to make it really nice and easy. Just so you know, when you get to 1b, it's not nice and easy usually. It's a lot of fun math. All right. So if I take a square root of both sides, that's going to give me a 2x up on top. That's going to give me a 2 minus x on the bottom. And the thing I usually forget to do is actually square root the 10. That would be a good idea, maybe. That's still square root. That's going to give me a 3.1623. At this point, we can now solve for x much easier. So we're going to multiply this to the other side. That's going to give us a 2x is equal to 6.32456 minus 3.1623x. Bring in all of our x's to the same side. So I'm going to add that to the other side. That's going to give me 5.1623x equals 6.32456. Dividing now. I can see how bad I did here with my made up numbers. Gonna give me an x value here of 1.23. First off, any questions on that? That is probably the simplest solving of that you can almost do. It does get way more complicated, but we're not going to get more complicated in here for sure. But if you take 1b, enjoy the quadratic formula, by the way. So if you haven't done that in a while, before you take 1b, you should reference yourself there and review yourself. So what is this x value? This x value is actually this x value here. That is that x value here. It is that x value here. It is all the x values in our table. And because now that we know that, we could actually solve for the equilibrium concentration of A. So A in this case at equilibrium, which is this, would be 2 minus our x value, which would be 2 minus 1.23, and these are molar. So it's going to get us here 2 minus 1.23, 0.77 molar. Our B will actually be the same in this case. It's going to be 2 minus x, which would give us 2 minus 1.23 molar, 0.77 molar. And now for our AB, our concentration of AB at equilibrium actually equals 2 times x, which means we would take 2 times 1.23 molar, and that's going to give us 2.46 molar in this case. First off, any questions on that? Those would represent the equilibrium concentrations of these guys when it reaches there. We had a large value of K, right? which means we should mainly have products at equilibrium. And that's what we have, right? We have 2.46 molar. We also have less reactants. We also see that our reactants started at 2, ended here at 0.77, decreased with time, which is what we would expect to happen, right? And this guy obviously increased with time as we started at 0. One of the nice things about this, which you might find out when you take 1B, is it is math, which means you can make sure you didn't screw up your math. Because I have the equilibrium concentrations, I could actually put it back into my equilibrium expression and check that I didn't screw up. So if I take my equilibrium concentration of AB that I just calculated and square it and divide it by the equilibrium concentration of the other two, I should hit 10. Yeah. And you get like, won't be perfect, but you get like 10.2 with rounding. It's pretty good. So you can actually check yourself at the end by taking your equilibrium concentrations, put it into the equilibrium expression, and you should get in the ballpark of your equilibrium constant. It probably won't be exact because you did some rounding and stuff like that. But it definitely, for example, if I put it back in and I got like 40 or 120, I definitely screwed up somewhere in the math. Yeah. So it should be in that 10 ballpark in this example. Any questions on that? Yeah.
So for this, are you saying we could like memorize this? We're gonna be doing this, or is this like exposure for this kind of stuff?
I'm gonna say we're gonna do basic ones. If any, it would be something like this. When you get to 1B, you will, that's pretty much all you do is this type of calculation. By the way, this is the calculation for 1B, pretty much. That's the entire calculation. Again, there's different ways to solve for, like I said, you'll be using like quadratic formulas to solve it and stuff like that. So the math gets a little crazy, some of it, but this is the major calculation there. So why don't you try one maybe and see how you do. Let's say we had this reaction, the one we were just looking at. What is the equilibrium concentrations of everybody if we started at 0.2 molar for each of them? Our I2 and 0 for our HI. That's going to tell us here that essentially this reaction should have only one option. It has to go in the forward direction as we only have reactants. And that is going to, again, allow us, like I said, and probably 99% of the time, your minuses are going to be on your left-hand side and your pluses are going to be on your right-hand side. So this would be minus x. Again, the coefficient here is 1. This would be minus x. The coefficient is 1. This would then be a product, which would be plus 2x as the coefficient is 2. And again, as I mentioned earlier, that is really important. Otherwise, really, you will not have the right mole-to-mole relationship and you will get the wrong answer. At the equilibrium step, we're just going to carry everything down. And again, at this point, we're just going to go into our expression here and solve for x. So this is again going to give us a 2x squared divided by our 0.2 minus x and our 0.2 minus x. And that's going to equal 50. Once again, if it's this class, it's probably a perfect square, if you even see it. And that will give us here 2x on top, 0.2 minus x on the bottom. And again, we want to make sure we do square root the 50 here. And that's going to give us 7.07107. We're going to multiply to the other side, our bottom, and that's going to give us 2x is equal to 1.4142 minus 7.07107x. Adding that back to the other side, going to give us 9.07107x equals 1.4142. Dividing here to finish it out, going to get us here 9.07107. An x value of 0.156 in this case. First off, any questions on that there? Yeah.
When you're multiplying the 0.00 minus x, are you just multiplying, like how are you substituting the x in a calculator?
Are you talking about like this step here?
No, the one.
This step here?
No.
This step here?
Yeah.
Yeah. Okay, so I'm taking what's on the bottom and I'm basically doing this, right? I'm multiplying it by 7.07107. So I'm just gonna on my calculator take those two and times them by each other. I'm just gonna multiply those two, right? And that will give me this number here. And then basically this is just 1x times that, and that's why this stays with it, and they get the x there, yeah.
Minus.
No, I just do it. I do it separately. I really just put this guy times this guy in, because that will give me the number I need. Because this is really just one, it's really just the same number, right? You just got to put the x on it, yeah. And it's still minus because this is technically minus x, right? So it's basically minus 1x. So it's basically minus 1x times this number, and that's how the minus still stays there, yeah. Other questions? All right, so now that we do have the x, that again is every x that we see in our ice table, and that's going to allow us to get to equilibrium. So the concentration of H2 at equilibrium is 0.2 minus x, which is 0.2 minus 0.156. And again, this is molarity, so we do want to put some units on it at the end there. It's going to give us 0.044. I'll call it 1 molar. That's going to be the same for our I2 since they're basically the exact same thing. 0.2 minus x, 0.2 minus 0.15x, 0.0441. And our HI is equal to 2x. So our HI at equilibrium is equal to 2x, 2 times 0.156 molar. Could give us a 0.312 molar as the equilibrium concentration of that guy. Once again here, if you wanted to just double check you didn't mess anything up, you could put all three of these values back into our equilibrium expression. If you did that, that would give you K is equal to 0.312 squared divided by 0.0441 and 0.0441. If you do that, you hit a 50 basically. So everything hopefully went right. Yeah. So it's a good way to check yourself. Question on that. All right. Now, there is actually an equilibrium expression, which is known as KSP. And KSP stands for the solubility product. And when you get to this for real in Chem 1B, it is the hardest part of the class. That's right there in the hardest part of the class. What is KSP? It is still an equilibrium. It's actually a special type of equilibrium. It's an equilibrium for things that if you remember your solubility rules, it is an equilibrium for things that are insoluble. So even things based on solubility rules that are basically insoluble, they will actually break apart a little bit in solution and create an equilibrium. So for example, if you had silver chloride, which based on solubility rules is a solid, in solution though, a little bit of it will break apart into silver ions and chloride ions. And when we write equations for KSP and things that are insoluble, that is always how we write the equation. And what I mean by that is always on the reactant side in this KSP situation, you always have the solid guy, the thing that's insoluble, like silver chloride. And always on the product side, you have aqueous ions, like we have up here. Aqueous ions, solid on the left. And what that means is when you write the KSP expression for this, we do products over reactants, but we do not include solids. So pretty much the KSP is always just the product side, which for this guy would be silver times chloride, would be the KSP expression for this reaction here, as once again, we do not include the solid in this case. You could actually do an ice table calculation like we just did, and you could calculate the solubility of silver chloride in water. And if you went through that calculation and calculated the solubility of silver chloride in water, you would actually see that it is 0.002 grams that you could get to dissolve in like 1,000 milliliters of water. So you get like a super, super small amount to dissolve. And that's why we consider something like silver chloride to be insoluble, because you can only get like 0.002 grams of it to dissolve in 1,000 milliliters of water, or 1 liter of water. That's a lot of water. So here's an example. We do write it exactly like before. If you have a little bismuth 3 sulfide and it breaks apart into a couple of bismuths and 3 sulfides, you once again, like normal, need to take the coefficients as the exponents. And again, we see our typical solid on the left, aqueous ions on the right. So that is typically what we see here. So for example, if we wanted to know what is the concentration of lead in water, we can use our ice table approach here. This is lead 2 chloride, which is insoluble based on solubility rules. Remember, chlorides, bromides, and iodides are soluble in everything except silver, lead 2, and mercury 1. So if you have those, they are insoluble. This will give us a lead with a +2 charge and 2 chloride ions here. We would actually do our ice table like normal. Initially, we're not even going to worry about the solid because it's a solid, it's not included. We have 0 of this guy and 0 of this guy. The change here would actually be normally on the left-hand side minuses, but this would then be plus. And I'll use X here, but when you get to 1B, they'll use S, which stands for molar solubility. They'll actually use a different letter, but we'll use X here. It doesn't really matter. At equilibrium, I'll squeeze it in there, we basically have X and X. If we take our KSP, it is the concentration of lead, and it is the concentration of chloride, which needs to be squared. We are looking for what is the KSP value in this case, right? So what they did tell us, though, is the concentration of lead at equilibrium is 1.6 times 10 to the minus 2. If I look at my ice table, what does lead equal at equilibrium? Lead equals X. So we actually know what X is from what they gave us, 1.6 times 10 to the minus 2. By the way, this would be plus 2x and plus 2x there on the bottom, which should be a better move there. And if we put this into our expression, this would be x, and 2 times x squared would equal our KSP. Now putting in our x value here, which is 1.6 times 10 to the minus 2, taking 2 times 1.6 times 10 to the minus 2 and squaring it will give us our KSP in this case. And again, all we're doing is putting x into here and x into here, basically. And that would get us here 2 times 1.6 to the minus 2, hit equals, then square it, hit equals, times it by 1.6 to the minus 2. Going to give us that number there that's circled, hopefully, 1.6 times 10 to the minus 5 is our actual KSP value in this particular case. So you could use an ice table like we did here, and again, basically substitute in there the value of X since you already know what it is, and you could get the KSP. You could also do a question like, you know, what is the solubility of this guy? And you could do it just like we did before. Questions on that there. All right. So let's show you that here, which is silver chloride. So this is our silver chloride equilibrium. And our KSP in this case would be our silver ion and our chloride ion. They again, in this case, gave us the KSP, which is 1.6 times 10 to the minus 10 10 to the minus 10. So again, we could do an ice table 0, 0. I'm not going to worry about this guy at all. I'm not going to put an X there, but I'm not going to worry about it because it is solid. Change is going to be plus X, which means at equilibrium, X and X. Again, normally this would be our minus side, but we don't have to worry about it because it's a solid. This is going to go into our expression, which gives us X times X is equal to 1.6 times 10 to the minus 10. That's X squared equals 1.6 times 10 to the minus 10. That's going to be a square root of that number, which hopefully is the number they have highlighted there, I think. And that's 1.3 times 10 to the minus 5 molar. And by the way, that is molarity, by the way, and that would be what is referred to as the molar solubility of silver chloride. It is molar solubility because it's molarity, which means it is 1.3 times 10 to the minus 5 moles per liter. If I wanted it in grams per liter, how do you go from moles to grams? You use the molar mass from the periodic table. So here, if we wanted to convert that into grams per liter, we would go to the periodic table, 107.9 maybe for silver, 3545 for chlorine. We would actually times it by the molar mass here of silver chloride, grams per mole. And that would actually give us here the number I was talking about a second ago, that the solubility of silver chloride in water is 0.002 grams per 1 liter. That is a very, very small amount, right? That basically means you could dissolve 0.002 grams of silver chloride in 1,000 milliliters or 1 liter of water. That's essentially nothing. And that's why we consider something like silver chloride to be insoluble based on the solubility rules. It does also give you a really good idea, something you should keep in mind as you go to 1B eventually, that even though, again, based on solubility rules, it says that you should always get a solid when you put those two things together. There's a lot of factors that affect whether or not you'll actually see the solid, things like pH, things like concentration, things like other ions that are present. So there's a lot of things that actually affect whether or not, the solubility rules will come true. Sometimes people think the solubility rules are always 100% exactly what it says. Like if I have silver chloride, I should have nothing but solid. But there's a lot of factors that actually play into play as to whether or not you'll actually see all solid or just a little bit of solid. Any questions on that? Yeah.
I disabled the change part, everything, is it correct that everything on the left side is negative and then everything on the right?
I'm going to say it is correct in almost all the situations. It would definitely be correct in any situation in our class. But when you do get to 1B, there are very rare situations where the reaction can actually be heading in the reverse direction. And that would flip your minuses and stuff. Because, for example, let's just say hypothetically, this reaction was going this way. That would mean over time, these guys actually would be decreasing and this guy would actually be increasing. And then we would have to actually change our minuses and pluses. But I would say probably even in 1B, probably 99% of the time, you can almost just automatic go minuses and pluses and you'll be correct. But there are certain situations where it can actually go in the other direction. But usually, even in 1B, when you actually do this for real, you don't really come across it all that much. So most of the time it's heading usually towards the product side. Yeah. Other questions on that? All right. That is, as they say, Chem 3 for the season. Yes. Any questions? All right. So here's where we're going. We're going to start reviewing now of what we talked about this semester. A reminder that the final exam will cover all the chapters that we talked about. And again, obviously here you are responsible for everything that you're supposed to know. So we're just going to kind of go through the chapters a little bit today, and we'll do a little bit more on Wednesday, and we'll see where we get. Just kind of hit the highlights of all the chapters, especially some of those earlier ones. It's been a while since we've gone through them. So we'll start here. I guess there really wasn't much in chapter 1, so we'll start with chapter 2. Remember, chapter 1 was just pretty much the scientific method, so that was the only thing you had to worry about. So chapter 2, we really got into it, and the main part of chapter 2 was measurements that we talked about to start with. And remember that when you do take a measurement, you always want to take it to the proper number of digits. And if you have some type of scale, you always want to look at the scale and you want to figure out again how far you can take that reading to. So remember, there are large markings like we've talked about before. And again, in this case, it is 1 centimeter. There are smaller markings, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And if you take that large marking divided by the 10 smaller markings, that's going to tell you that each of the smaller markings is 0.1 centimeters. That means when we take a reading, that's 1.1, 1.2, 1.3, 1.4, 1.5, 1.6. There should be some numbers that everybody agrees upon. In this case, 1.5 are all our certain numbers. There's always an estimate, so we want to make that estimated guess based on where it's at. In this case, perhaps it looks like it's a little further than halfway there. So maybe we do a 7 in this case, and always the units, and that's our first uncertain number, right? Remember that you could do the tolerance of a measurement, like the question on the exam there, by taking the smallest markings and dividing it by 2. That's what gives us our plus or minus 0.05 centimeters, which means we can't take this to 2 decimal places, which means the proper reading here, 1.57 centimeters plus or minus 0.05 centimeters in this case. Again, with the reading and its tolerance. Remember, when you divide that smallest marking by 2, it tells you essentially how far you should take the reading to. And in most cases, it usually is one more place to the right of the smallest marking is essentially how far you could go. Not 100% of the time, but most of the time you can always go usually one more place to the right. The reason we always record all the certain numbers plus the first uncertain number, right, is that is what significant figures are, right? And significant figures typically come from a measurement, and they basically include all those things, that all the certain numbers and that first uncertain number. That led us into talking about significant figures for a good chunk of the chapter. So a couple of reminders, which I hope they're just reminders at this point, is when we count sig figs, all non-zeros, right, are significant figures. When we talk about zeros, there's a few different types of zeros. We have the leading zero. And those, for example, are all the zeros that come before the first non-zero number. And by the way, again, that is when we start counting, is when we hit the first non-zero number. Leading zeros are not significant. So again, in this case, this guy would have 3 significant figures. We have some trapped zeros, or captive zeros. Those are significant. And again, those are any zeros that are between 2 non-zero numbers. So again, we start counting at the first 4 and at the second. This guy would have 4 significant figures. And then there are trailing zeros, which is the one that gives people, again, the hard time. And they can be significant or not significant. And it depends on if there is a decimal place, right, in the number. So if you had 400 written like this with a decimal point, that would make those zeros significant, and we would have 3 significant figures. If you wrote 400 like this, then it would have 1 significant figure, as the decimal point is not written in this number as well. Any questions on that there? Now, with this, we talked about also scientific notation, right? And scientific notation, again, is a number between 1 and 10. And again, it has to be a number between 1 and 10, not less than 1. This is either a positive or a negative number, depending on which way you need to move the decimal point to get yourself to a number between 1 and 10. So 1, 2 places, 4.25 times 10 to the 2, 0.00240. 1, 2, 3 places to the right, 2.40 times 10 to the minus 3. Remember that whenever you write a number in scientific notation, all the numbers before the times 10 part are always significant. So we do not want to lose any significant figures, as we talked about. This has 3 significant figures. This would also have 3 sig figs. This has 3 significant figures. This also has 3 sig figs, which is why we have to keep the zeros. Probably more important in terms of scientific notation, as we've talked about many times throughout the semester, do not forget about your exponent buttons, right? So again, you want to always make sure you are using the proper button when you punch those in, along with, if it's a negative, that you're using the proper negative button and not the subtract button, right? So again, you want to make sure you're punching those numbers in to your calculator correctly. Yeah. Now, in terms of sig figs and calculations, we also talked about, again, a reminder that if you multiply or divide, we are looking at significant figures. So the number of sig figs in your answer matches the number of sig figs in your calculation, the lowest number of sig figs. So the lowest number of sig figs is what you're looking for. So the low sig figs is how many sig figs your answer could have. If you're adding and subtracting, it is different, right? You are not looking at significant figures, but you're looking at decimal places. So the number of decimal places in your calculation is how many decimal places you have in your answer. And remember, again, here it is the lowest amount, or smallest amount, I guess is the better way of putting that, the smallest amount of decimal places. So once again, if you added 1.20 plus 2.4 gives you 3.60, 2 decimal places, 1 decimal place. The answer here should be 3.6, which has, again, 1 decimal place, but 2 significant figures. So you want to keep that in mind. Also, if you're doing multiple calculations along the way, you want to keep track of your significant figures, right? You don't want to round too much. Keep a few extra digits, and then you should clean it up at the end. If you're doing some type of combo thing, you do want to just follow what you did in the order you did it. Here we are multiplying up on top, so we should actually end up with 2 significant figures. Here we then have 3 significant figures, and we're dividing at the end, which means we should end up with 2 significant figures when it's all said and done. So you want to kind of keep track of it as you go through your calculations. Yeah.
Yeah, well, that's like something that add it.
Yeah.
For example, like, with like, if you get the big there.
Exactly. I personally would do 1.2 times 4.222 hit equals. And really for the top, it gives you something on your calculator, 5.0664. And then we're going to take that and divide it. Personally, I would take the whole thing on my calculator. But technically speaking, you do want to keep track that it actually should end right about there. I personally don't know if I would round at this point to 5.1, but I would take the whole thing and then divide it out by 0.444. And that gets you some number like 11.41081.081. At this point, I can then clean it up to here, which actually would be 11 in this case, right? based off the top one. So remember, you could keep a few extra digits. You can always kind of keep a digit or two, put a line over where you should end up just to kind of keep track of it. But you do want to kind of keep track of it. And you definitely don't want to round too quickly. Otherwise, again, you may have some rounding errors in your answer. Other questions? All right, so we did that. We got into conversions, right? And some conversions and prefixes are sometimes used. For example, nano is 10 to the minus 9. And remember, when you have something like that, our centi is 10 to the minus 2. When you have those numbers, again, if you want to use them as a conversion factor, for example, in meters and nanometers. So this is really the base unit and the prefix unit, right? So when you see that, remember that is one of the prefix units is how much of the base unit there is, right? So it is 10 to the minus 9 meters in 1 nanometer, not the other way around, which again is a common error people make. And same thing here, it would be, say, if we were doing meters, 10 to the minus 2 meters equals 1 centimeter in one of the prefix units. That again is a equality. And remember that for any type of equality, we could write conversion factors for it, right? And conversion factors, right, are just fractions. So we could say there's 10 to the minus 2 meters over 1 centimeter. Our 1 centimeter is 10 to the minus 2 meters. By the way, on your calculator, 10 to the minus 2 is 1 times 10 to the minus 2. So again, you would punch it in like you were doing scientific notation. If you needed to on some calculators, you would go 1, your exponent button, your negative button, and 2, and that would be, again, how you would put that in. We use equalities and conversion factors to do problems. And for example, you could have 1 pound is equal to 453.6 grams. And in this particular case, we would have 1 pound up on top, 453.6 grams on the bottom, or 453.6 grams over 1 pound. We set it up this way using dimensional analysis, right? Using conversion factors so that units cancel. So that was a big thing out of chapter 2, right? And that is basically how they want you to show all your work in chemistry. And again, if we had those two conversion factors are 453.6 grams per pound, or a pound is 453.6 grams. And we had 36.5 grams. We would use it opposites cancel, so 453.6 on the bottom, 1 pound on top. Remember, when we do this, even though it's not written as a fraction, it is sort of fraction-like. Anything on top gets multiplied, anything on the bottom gets divided. Opposite units cancel, right? And whatever you're solving for does need to be up on top by itself. Otherwise, if it's on the bottom, you're doing the inverse of what you're looking for. That gives us 0.0805 pounds in this case. Sig figures wise, remember this guy here has 3 significant figures. They call that an exact number here. So remember, we have exact numbers and measured numbers. Exact numbers are our definitions, or they are things that are counted. And when we do calculations that involve exact numbers, we don't worry about the significant figures in there. So this would be a case you wouldn't need to worry about the conversion factor. And in most dimensional analysis problems, that oftentimes will sort of get you back to the original number is pretty close to the right number of sig figs you should have. And that's because when you set it up in dimensional analysis, all you're doing is multiplying and dividing. So you're all looking at significant figures only in this particular case. Again, if you had one that was not considered an exact number, then you would have to look at it. And usually in that case, you would look at the number part, not the one part of it. It would be just the number part for the sig figs. Yeah.
That number you don't want.
You don't worry about it. So something like this, something like, we had like 450, say, nanometers, and we're doing 1 nanometer is 10 to the minus 9 meters, and we're looking for meters. These guys would cancel. And again, here, this would be 450 times basically 1 times 10 to the minus 9. Going to get you 4.5 times 10 to the minus 7 meters. And in this particular case, this would definitely be an exact number, so we're not worried about this at all. We would default here. This has only 2 sig figs, which is why in scientific notation here we would go 2 sig figs. Yeah.
I think if I remember correctly, they were all exact numbers except for the conversion.
Uh-huh.
Is that correct?
There are a number, but most of the time, I would say it's almost fairly safe to look at a conversion and probably think that it's an exact number. Um, but there are some that are not. There are a few that are not, but most of the time they definitely will be. But it's really the difference here. If you're doing anything that is an English to English conversion, that's going to be an exact number. If you're doing anything that is a metric to metric conversion, that also is going to be an exact number. It's really when you cross over metric to English. So like, for example, whatever it is, 946 milliliters in a quart or something like that. So when you kind of cross over from those two, those you typically have to look at. There was only a few here in this college that they go with. This is one of those crossover ones that you don't have to worry about. And then the most common one is 1 inch is exactly 2.54 centimeters. That's also an exact conversion. So you really only should take probably a look at it if you're doing that sort of crossover from English to metric, and it's not the 1 inch or at this school, the 453.6 grams and stuff like that. That's the one that you need to look at. And again, like I said, in that case, there usually will be in this conversion, one of the numbers in that conversion factor will be a 1, and the other one will be a real number. And you should look at the real number, not the 1 part of it. So, like for example, if it says like 1 quart's 946 milliliters, or something like that, you would look at the 946 or something like that to determine it. Other questions? Or if you had, like, for example, kilograms to pounds, you would look at the 2.2 number versus the 1 kilogram. All right. So we did that. We did dimensional analysis. Then we also talked about, obviously, density, I think, in this chapter. And density has a formula. Density is mass divided by volume. Remember the DMV triangle, maybe that helps you rearrange. That means mass is equal to volume times the density, and volume would equal mass divided by the density. The units of density are grams per milliliter, are grams per cubic centimeter. Those are the two very common ones. And these are usually the common ones for solids and liquids. Although we don't come across it too much in this class, when you get to gases, which you'll get next semester, density is sometimes given in grams per liter for gases. Now, you could obviously use this like normal as a formula and solve for anything. Very common as well, right? 1 milliliter is equal to 1 cubic centimeter, right? That is the same sort of situation. There are a few different ways we could get the volume of an object, right? One way is, frankly, we could just take a reading, right? Read the meniscus. We could actually read the milliliters. Also very common is we could take 3 length measurements, length times width times height of something like a solid cube, and get the volume, and each of them are in centimeters. we could get a volume that is a cubic centimeter. A reminder that if you take basically any type of length measurement in cubit, for the most part, a lot of times that's a volume. So remember that is a volume. And then probably the most common way for density that we get volume is volume by displacement. So remember, if you have like water or something in a container, you put a solid in there, it will displace a volume that's equal to its own. So you basically take the difference in the volume, and the volume of the object will equal the final volume minus the initial volume. So that's a very, very common way, that volume by displacement, to get the volume of an object. Also, if you are given the density, you could use it as a conversion factor and do dimensional analysis. So remember, you had like a density of 1.3 grams per milliliter. You could use that as a conversion factor of 1.3 grams over milliliters, or a milliliter over 1.3 grams. You could do a dimensional analysis, as we talked about a number of times throughout the semester. By doing a dimensional analysis type of approach, you don't have to worry about rearranging formulas, right? Because it kind of does it for you. Because if you use it like a conversion factor, anything on top gets multiplied, anything on the bottom gets divided. So you don't have to worry about, did I rearrange like the equation correctly? As long as you set it up, opposites cancel, units cancel, it'll kind of do all that for you. Any questions on that? Yeah. It is. Any length measurement is really a that's cubed is a volume measurement. So for example, if you had like meters cubed, decimeters cubed, all those guys, they're all volumes. And they come from 3 length measurements though. So if you had an individual just centimeter by itself, not cubed, it's a length measurement. And then if you kind of cube it, kind of like the very early experiment we did, right, where you had the wooden block, right? And you took 3 measurements in 3 different directions. And that was the way we were able to get the volume of that particular block. Yeah. Other questions? Okay, density, density, density. That is chapter 2, I believe. The highlights. Then we are off to perhaps chapter 10. Oh no, we went 3 actually next, I think. So we went to chapter 3 next. And chapter 3 was about really states of matter. So in chapter 3, we talked about states of matter. So obviously we have solid, where everybody's packed in there relatively tight to one another. We have the liquid, right, where everybody's a little bit more moving around, a little bit more spaced out. And then we have the gas phase, where everybody is flying around as you go through it. And remember that as we go from solid to liquid to gas, those are all processes that are endothermic, requiring energy to be put in. And if we go from gas to liquid to solid, that is exothermic processes. Energy has to be removed. There's also the change of phase that we talked about, and change of state. Remember, as we go from solid to liquid, that is melting. As we go from liquid to solid, that is freezing. Liquid to gas, that's evaporation or vaporization. Gas back to liquid is condensation. Going from solid, skipping liquid and going directly to gas, that is sublimation. And going from gas back to solid, skipping the liquid as well, that is deposition. All right. And those are the changes of phase that requires energy to do so. As we talked about in a couple places, this occurs at the same temperature. That's the normal freezing point, melting point. For example, for water, that's 0 degrees Celsius. Evaporation and condensation occurs also at the same temperature. That is the normal boiling point. So remember, it just depends on what you're doing at that point as to what's going to occur. If you're exactly at the normal boiling point, for example, for water, which is 100 degrees Celsius, you have both phases happening at the same time, as we talked about in the previous chapters. And It's not until you get a little bit above or below that temperature that you fully transition phases. We also talked about a couple other things in this chapter, which were, I believe, we had elements, we had molecules, and we had compounds, right? And these are all, sometimes pure substances. Elements are the basic unit of everything, right? And we find them on the periodic table. Remember that molecules are a basic definition of two or more atoms together. They can be the same elements, they can be different elements, but basically for something to be a molecule, all you need is two or more atoms. A compound, you need two or more atoms of different elements, right, involved. So for example, again, we could have something like H2N2, right? O2, Br2, Cl2, I2, and F2. These are all molecules. These are all what are referred to as diatomic molecules. And that's because they all contain basically two or more atoms together. In this particular case, though, they all contain the same element, and these guys would also be elements as well. These are how these 7 elements come from the periodic table. If they are by themselves and not attached to anybody else, a reminder that everybody else on the periodic table comes as ones, right? They just come by themselves. And by the way, as we also talked about in a number of chapters, things on the periodic table that are by themselves uncombined do not have charges. So they don't have charges either, right? So that is different than, say, something like H2O. H2O is a molecule. It is also a compound because it contains atoms of 2 different elements. H2 obviously is not an element because it has 2 different elements involved, right? So again, that is the major difference between molecules and compounds. Molecules can be 2 or more of the same or 2 or more different. They're all molecules. But for it to be a compound, it has to be 2 or more of different elements coming together for it to be a compound. And obviously H2O would not be an element, just like H2N2O2 would not be a compound because it only contains one type of element. Any questions on that? Now, when you have these guys together, or not really together, but separately, and just have a little bit of each of those, remember those are what are referred to as pure substances. And a pure substance can be an element, it could be a compound, it could be a molecule, obviously. But it's basically a pure substance is just one thing by itself, nothing else with it. So for example, if you just had water, that is a pure substance. It's just water. There's nothing else there with it. It's just one thing. If you had, just iron metal, right, by itself, that would be a pure substance as well. Now, what we also talked about in this chapter is if you take 2 pure substances, 2 or more pure substances, and you put them together, you get what are known as a mixture, right? And a mixture is a combination of 2 or more pure substances. There are a couple of different types of mixtures we talked about. We have homogeneous mixture, which means everything looks the same throughout. We have a heterogeneous mixture, and we see different layers or phases. So for example, if we took some sodium chloride solid and we put it together with some liquid water, that is a pure substance of sodium chloride. That is a pure substance of water. Once again, if we put it together, the sodium chloride will dissolve in the water and make a sodium chloride solution, which is a homogeneous mixture. So the mixture there is our sodium chloride solution. you can't really see the sodium chloride anymore at that point. It just looks like water basically in there. Now, if you took something like pieces of iron metal, right, and you mix it with sand, right? Pure substance, put it together, you get basically your iron in your sand, right? And that would be a heterogeneous mixture. You could do whatever you want in that case. You will always see the metal in there, just like if you took sand and water and put it together, right? You can mix that all day. The sand is never going to dissolve in the water, so you always see the sand particles. So remember, a heterogeneous mixture, you always see sort of different layers or phases, rather than a homogeneous mixture where you see both, just see one really. Everything looks the same throughout. Any questions on that there? Yeah.
They say that they also don't have charge. They're right.
Yeah, I would say in most cases it's probably going to be neutral. I think in most cases, yeah. Yeah,
The heterogeneous mixtures, is it safe to say that they never mix?
that is safe to say. Yeah, they never mix. You could mix as much as you want, but even with sufficient mixing, you will still see the different components basically of it. Yeah, and they won't really come together. Now, remember that regardless of what type of mixture you have, um, that is a physical change, right? And remember that a physical change is basically what you start with and what you end with are fundamentally the same thing. And that's different than a chemical change, which was also in this chapter, which is basically a chemical reaction. In a chemical change, what you start with and what you end with are different. New things were made, basically. The key to that is you cannot get back your original components by any type of physical means. You can't boil, freeze, whatever it is. You can only do that through a chemical change. So remember, like dissolving our sodium chloride in with our water is again actually a physical change to make that sodium chloride, not really a chemical change. But if you took something like magnesium plus some oxygen gas and lit it on fire, but did not look closely to observe what's going on, this is a chemical change that you cannot get back the original stuff that occurs. So remember, any type of phase change, when you're just changing something from one phase to the next, that's always a physical process. Making these mixtures are also physical, and we know that because we could use some type of physical means to separate them out. So the two popular ways is filtration, right? And filtration works really great with a solid and a liquid. And you put a piece of filter paper up there. You take your mixture that's got a bunch of stuff in it and you pour it in. And what's going to happen is, again, the liquid part should come through and all the solid should end up on the filter paper. So just by that physical process of separation using a piece of filter paper, we're able to separate out both parts of our mixture. And remember that when you do make a mixture, they do retain their identity. So here we could get both parts back by just doing something simple like that. Even with a homogeneous mixture, you could do something like distillation, or to a lesser extent what you did in an evaporating dish. But in distillation, you have kind of a closed system, as we talked about. You have something like salt water, which is a homogeneous mixture. And this is really cold, this kind of tube that ties both sides. As you start heating this, because the salt water is basically sodium chloride and water, sodium chloride is an ionic compound which is held together super strongly, and you could heat the heck out of it and it's not going to go into the gas phase. But for water, all you'd have to do is heat it up to about 100 degrees Celsius, and that is enough to start to evaporate off your water, right? You're going to create steam. And that steam has nowhere to go but through this cold spot, and steam that goes through cold will then go through condensation, and you can continue this process until you basically evaporate off all the water, and you'll just be left on this side, which is the salts, and over here we'll get basically all the water over here. So even a homogeneous mixture where you can't really see both components, you could use the advantages of difference in like boiling points, which are physical properties, to separate out something. And that's what we do when we try to separate out mixtures, is take advantage of differences in physical properties, boiling points, melting points, size, and stuff like that, to allow you to separate out things. Any questions on that there? That was chapter 3, I believe. After chapter 3, we went ahead, I think, to chapter 10. We got into some fun chemistry, maybe. I don't know. Probably not. And in this chapter, it is energy. So we talked a lot about energy and different types of energy. And one of the things, obviously, we talked about was types of reactions, which are our exothermic, as we've been talking about. And again, energy is released. And usually, as we talked about, any type of energy value that you calculate that's negative usually implies an exothermic process occurring. Endothermic is energy is absorbed, and usually in that case, it's more of a positive value that we see here. And we also looked at some energy diagrams, and we also saw them here in this last chapter again. So a reminder that when we look at energy diagrams and you're looking at your reactants to your products, if your reactants are higher in energy than your products, that's going to be an exothermic reaction. And remember that there is that hill that reactants has to climb to get to the other side. That's our activation energy. And also, again, the difference between the reactants energy and the products energy, that is our delta H for the reaction, or our change in enthalpy. And that is the guy that if it's negative means it's an exothermic reaction. And as we talked about, right, one way to calculate delta H of the reaction is the delta H of the products minus delta H of the reactants. That's your final state minus your initial state. And that's different than when we look at a graph of an endothermic reaction. It looks a little bit like this, maybe. Reactants to the products. And this would be an endothermic reaction, as our reactants are lower in energy than our products, so energy has to be put in there. Once again, this is our activation energy here. And the difference in the energy of our reactants to our products is our delta H, which will be a positive value here and a negative value in this particular case. Any questions on that there? Now, let's see. We did talk about enthalpy, which is our change in delta H. So again, delta H is our change in enthalpy. Remember, it's a state function, which means you could calculate the delta H of the reaction by going to the table, taking all your delta H of your products, and subtract your delta H of your reactants. And in this particular case, in this particular case, what we would do is go to the table. And remember, as we talked about, it's important when you do go to the table that you do find whatever you're looking for in the right state. So if you had something like 2A plus B goes to 3C, and again, you look in the delta H of formation table for A, B, and C, and they tell you, hey, it's minus 32 kilojoules, plus 125 kilojoules, and minus 45 kilojoules. To calculate this, you would do your products minus your reactants. And you do need to make sure that you take into account the coefficient as well. So our delta H of this reaction would be 3 times our value we find for C in the table, minus 45 kilojoules. That is pretty much all of our products, minus our reactants, which is 2 times our A, which is minus 32 kilojoules, plus our B, which is 125 kilojoules. And if we add all that together there, uh, we end up with an answer of negative 196 kilojoules. In this case, it would be exothermic because of the negative value for our delta H in this case. So again, it's important to take into account the coefficients as you're doing this delta H. Any questions on that there? Now, if you ended up with a positive value, obviously for delta H, then it would be more of an endothermic reaction. Energy is being absorbed. We got into specific heat, I believe. And we had a specific heat equation, Q is equal to ms delta T. Remember, specific heat is the amount of energy required to raise 1 gram of a substance by 1 degree Celsius. Yeah. So in this formula here, Q is our heat, our energy, and that has units of joules or calories. Remember, joules and calories are the 2 common units of energy. Probably joules used the most, and kilojoules as well. Relationship, right? 1 calorie is 4.184 joules. That also is the specific heat of liquid water, which is a number they want you to remember. M is our mass in grams. S is our specific heat capacity in joules per gram per degree Celsius. Our calories per gram per degree Celsius. And remember, it's really important in this equation that the delta T is always your final minus your initial. And that is because the only way, for example, for us to get a Q that is negative has to do with the temperature part. So you just don't want to take the difference. You want to take the actual final minus initial. And that's because if Q is negative, it's exothermic. And if Q is positive, it is endothermic. So when you do your final minus initial, it's important to do it that way because if you get a negative, it's really important in terms of the energy value. So whenever you're calculating any type of energy value, if it's positive, it should be positive. If it's negative, you should leave the negative in there. We talked about a relationship here and obviously the specific heat of liquid water is that 4.184 joules per gram degree Celsius. It also is 1 calorie per degree Celsius, which is basically this conversion here as well. We talked about sort of the transfer of heat and energy from objects at different temperatures. And we see that, for example, when we take a piece of metal, right, as we talked about, and we heat it up to say 95 degrees Celsius, and we dump it into some water here at say 25 degrees Celsius. When we put that piece of hot metal into here, because the metal is hotter than the water, heat always transfers from hot to cold. So it's going to give off that heat and energy to the water surroundings. That's going to be endothermic for our water, and we should expect the temperature to rise. It would be exothermic for our metal because it's giving off that energy, so its temperature actually should go down. And that gives us a relationship when we do this of Q of the metal is equal to minus Q of the water. And that negative is important because it gives us that opposite relationship that occurs. So in this case, you could, in a lot of cases, use the specific heat equation for water and solve for something, and then go back and use the specific heat equation for metal as well. So you could kind of use both of them there, and then kind of fall for whatever you're looking for, maybe a specific heat capacity of a piece of metal. Any questions on that there? Yeah.
Why, there's a negative in front of the two for water?
There's a negative here. Yeah. So let's just say, for example, we threw in some numbers here. We'll say we put the metal in, and this is our initial temperature, right? And we'll say the final temperature ended up at, I don't know, we'll go 27 degrees Celsius. And we'll say we had a mass of like 130 grams of water. And over here, this was our initial temperature, right, of our metal. And we have, say, a mass of, I don't know, 45 grams of it. What we know is after we dump that piece of metal into that water, it's going to release all that energy, and it actually will come to rest the metal's temperature as the same as the water, which means our final temperature here is 27 degrees Celsius. So when I would go into my water here, it would be like 130 grams. It would be 4.184 joules per gram per degree Celsius. And it would be our grams. That's a change in temperature, which I'll go below, which would be our final 27 minus our 25 degrees Celsius. So this is going to give us basically a positive number there for Q, right? If we do this, and in this case, get my bad made up numbers here. So we end up, with about 1087.84 joules. Now, the reason we have the negative here is if we want to know how much energy the water gained, that would be the number. So that water gained that number, which is why it's positive. Every single bit of that energy came from the metal. So for the metal's perspective, that is how much energy it lost. And because the metal lost that energy, that's exothermic for the metal, which means Q of my metal would be negative Q of my water, and that's going to turn this guy into a negative number. And that makes sense for the metal because it's releasing the energy and the water's gaining the energy. That's also really important when we go into, for example, our specific heat equation here for the metal. And if we do just the change in temperature part for the metal, it ended at 27 degrees and started at 95 degrees Celsius. That's going to give us a negative number for the temperature difference for the metal. And if we're solving for something like M, we need an actual negative value there for the Q, which we will now have, right? And those two negatives are going to cancel each other out when you solve for something like M is equal to Q, I'm not M, but S is equal to Q M delta T. This guy will be negative. This guy will be negative. That's going to turn our specific heat capacity into a positive number, which is what it should be. So those negatives are quite important in that case. Other questions on that there? All right. Then we also talked about, I think in that chapter, Hess's law. And Hess's law is when you can use a bunch of individual reactions to make an overall reaction. So let's just say, for example, here, A plus B goes to E plus F, and we wanted to know, how much energy, right, or enthalpy we need for this one. But we know that if we take C plus D going to A plus B, actually we'll do 2's on all those just for fun. And the delta H here is negative 100 kilojoules. And we know that C plus D goes to E plus F, and the delta H is, say, 50 kilojoules. So we want to basically add these equations together to end up with this equation. And remember that when we manipulate an equation that has a delta H with it, we have to do some things to it. So for example, if we have an equation and we simply reverse it, what we do with the delta H is just change the sign. So it goes from -10 to +10 in this case. If we need to multiply this equation by a common number, that would give us 2a plus 2b goes to 2c. How that affects the delta H is it will be -10 times 2, or -20 kilojoules in this case. So we have to multiply the delta H by whatever number we multiply the reaction by. If we need to divide, so let's just say we had to divide everybody here by 2, that would bring us back to the original equation. And basically we would take this and divide this guy by 2, which would get us then back to our 10. So if you have to reverse one of these reactions, you change the sign of delta H. If you need to multiply a reaction by a common number, you would multiply the delta H by that number. And if you need to divide by a common number, you would divide the delta H. So in this case, to get to this, we want to keep it really simple. So here A and B are on the incorrect side. I need to reverse that reaction. And that would give me 2a plus 2b goes to 2c plus 2d. And my delta H now would be positive 100 kilojoules because I reversed it. I also need to actually divide everybody by 2 because I don't want 2 of everybody. I just want 1, which would take me back to this equation. And that would give us a delta H that's equal to 50 by taking this and dividing it by 2. Now, the other guy I have in the right location, I could just leave him exactly the way he is. And at this point, I could add these together, and we're going to completely cancel out these guys. And that would get us our overall reaction of A plus B goes to E plus F. Now, our delta H in this case is going to be our, and again, we didn't do anything to this guy, so he would still be 50 in this case. So our delta H in this case is going to be those two guys added together. For 50 plus 50 kilojoules would give us 100 kilojoules for our added reaction. So with Hess's law, what we try to do is kind of manipulate equations, turn them around, multiply, divide. The goal is to just get everybody on the correct sides. And then once you have it on the correct sides, then you can add them together. And what we do at the end is just add up all the energy values after we sort of change them. Any questions on that there? One last thing we talked about, I think, with this is if we do have an equation, here, and we can have relationships that we could get from this equation, like, for example, using the coefficients here. And we could say for every 2 moles of A, we get out 50 kilojoules of energy. We could actually use that as a conversion factor that involves energy and moles. And we could flip it around and do 50 kilojoules up on top and 2 moles on the bottom in this particular case. And again, we could do that. So for example, if we were doing 4 moles of A and wanted to know how much energy we would get, we could just set it up as like a dimensional analysis problem. 4 moles of A, opposites cancel. We're going to go with this guy here. So 50 kilojoules per 2 moles of A. We get that from the equation, almost just like stoichiometry, essentially. The moles will cancel, and that's going to get us basically, looks like 4 times 50 divided by 2, 100 kilojoules of energy. And that does make sense since we're starting with twice as much as we did there we get twice the amount of energy out. Could also do this if you knew how many grams of A, right? Or grams of B or grams of C, convert it to moles and use it as a mole. You could do it for anybody in this equation. You could say that for every 1 mole of B, there is going to give you 50 kilojoules of energy. 4 moles of C will give you 50 kilojoules of energy, or 1 mole of D will get you 50 kilojoules of energy. So again, you can basically use any of those as conversion factors, and you can use the equation as a conversion factor as well. Any questions on that there? That is, I think, exam 1 stuff, yes. We're going to lay it up now.